Assalamu alaikum. In this series, Mr. Omar will guide you through some practice problems to cover all items included in the coverage issued by Emirates Schools Establishment, E.S.E. This is part 3. Have a fruitful time.
Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome again. We are in part 3 now with the 11th goal. On the following diagram, draw arrows at the points A, B, and C and D to show the direction of the magnetic field at these 4 points. The direction of the magnetic field is the tangent for the magnetic field line at that point, and it is directed away from the North Pole. So at A, draw a tangent and it will go away from the North Pole. At B, again, draw a tangent from north to south. Again, at C, we have the tangent, it is along the line itself, and it will point to the south as if it comes from north. Inside the magnetic field goes from south to north. It is opposite to the magnetic field elsewhere. So inside the magnet it is from south to north, don't forget that. Outside the magnet it is from north to south. Outside from north to south, inside from south to north. Don't forget that. Now question number 12. We need to apply the right hand rule to find the direction of the magnetic field or the velocity or the force. For this question, what is the direction of the magnetic force on a positive charge that moves as shown in the 6 cases shown in the figure? First of all, it is a positive charge. So apply your right hand rule without any problem. How can we apply it? The finger with the velocity, the thumb with V, index finger with V, and the normal or the middle finger outside your hand, it is the force. Now, for part A, V downward, so here is the direction of the thumb. The magnetic field is out of the page, so your index should be point to you while your thumb is down. If the index is pointing to you and the thumb downward, so the force is to the left. This is F, this is V, this is P. For part B, the velocity is upward, so the thumb is upward. Here is the thumb. The magnetic field to the right, so the index is to the right. Thumb up, index to the right, so the force is inside the paper. F is inside the paper. Here, V is to the right, so here is your thumb. The magnetic field inside the paper, which is indicated by a cross. If you put the thumb to the right, the magnetic field inside, so your index finger inside the page, so the force is up to the top of the page. Here is FB. D. The velocity is parallel to the magnetic field, so no force. E. The velocity is inside, so your thumb is inside the screen. Extend the index to the top of the page, so the other fingers or the normal to your hand is to the right. So this is FB. Here the velocity is out of the screen, so put your thumb out to the screen pointing to you, the index to the left with the magnetic field, so the force is downward to the bottom of the page. Practice this very well, if you please. It's very important to practice this, or the rule, or the right hand rule. Now, what is the direction of the magnetic forces on a negative charge? It is the same as before, same question, but the charge is negative. So all we need is to invert the force. For the first one, instead of to the right, it should be to the left, because the charge is negative. For the other one, B, it should be out. Practice your right hand rule. For C, here it is up. So because the charge is negative with the same situation, but the charge is negative, so the force should be downward to the bottom of the page. D, it is the same, no force, because it is parallel. The velocity is parallel to the magnetic field. For D, we have the same as D here. The force is to the right, so because the charge is negative, it should be inverted to the left. And for the last one, part A, question 1, it is downward, so here it is upward. So it is the same. You will apply the right hand rule in the same way, but you must invert the direction get by your right hand rule, because the charge is negative. Question number 3. An electron is moving at 4 times 10 to the 3 meters, so it is V, in 1.25 Tesla, this is B, experience a force of, this is the force, F, B, 1.4 times 10 to the minus 16. What angles, look, what angles or angle, let us see. It's important thing. What angles does the velocity of the electron make with the magnetic field? Put first the law, FB equals, for the moving charge, Q V B sine theta. Theta, it is the angle between V and B. Let us draw that. Suppose that this is the direction of B, and I don't know what is the direction of the velocity. Suppose it is like this or anything else. We need this angle. Now, FB, it is 1.4 times 10 to the minus 16. Q, for the electron, it is an electron. So the charge of the electron, it is 1.60 absolute value times 10 to the minus 19, the magnitude of the charge. I don't need the type of the charge because it will affect the direction. It will not affect the magnitude. So 1.602 times 10 to the minus 19. V in the question are 10 to the 3 and B 1.25 sine theta. Solve this equation to get theta. Theta equals sine inverse of 1.4 times 10 to the minus 16 divided by 1602 times 10 to the minus 19 multiplied by 4 times 10 to the 3 multiplied by 1.25. The answer would be 10 degrees. Okay. But we have another angle has the same sign as in trigonometry. This is theta 1. Theta 2, the angle that has the same magnitude of sine is 180 minus theta 1. 180 minus 10, which is 170 degrees. Like this situation, this is our magnetic field, and the other angle that has the same magnitude of force is here, 170. That's why the question told us to find the angles, not the angle. So every time if you have the force and you are to find the angle, find two angles. Immediately from the law, then subtract from 180 because we have two angles. The only difference is how it will be the spiral part of this. This will be spiral in this direction, and that one will be in the opposite direction. That's it. That is the only thing between the two things. The radius is the same, the velocity is the same, but the difference is the direction of the spiral. Now we need to find the torque on a rectangular loop. A rectangular loop, this question is in the book, a rectangular loop with a height of 6.5 and width of 4.5. The height and width. This is H, this is W. From these two information, I will have the area A equals H times W, or W times H. And don't forget to convert it into the meter, 10 to the minus 3 meter for the centimeter, 10 to the minus meter. In a uniform magnetic field of, this is the magnetic field, which points in the negative y direction. Now you must look to the graph. Where is the y direction? It is not up as we usually do. It is to the right. So the magnetic field is to the left. It is to the negative y. This is B. So the magnetic field B equals 0.25 Tesla, which points in the negative y direction. The loop makes an angle of 33 with the y-axis, as mentioned in the graph. The loop carries a current of, this is the current, in the direction indicated by the arrow. What is the magnitude of the torque? Please take careful for this. Be careful for this question. Let us look to this loop from positive z-axis. Here is the way that I'm looking down. I will see the y-axis here like this, and here is the magnetic field, and I will see this side W, only W, like this. This is W, and this is the angle theta. And the current is going up, then it will going from the z-axis out of the page in this direction. So this is the direction of the current. Why I am interested in this? Because I need to find the direction of the normal. The direction of the normal. It's a very important thing, because theta, it is matter in this question. Now to assign the normal to the loop, you need to put your four fingers of your right hand rule with the current from this point X to this point. I don't need X and Y. Let us be Q, P, and Q. So the index from B to Q, or the four fingers from B to Q, that leaves your thumb in that direction. Here is the thumb. Here is the normal to the loop. And here is the angle indicated in the equation. I will name it as alpha. What is alpha? Let this angle be gamma. Theta plus gamma, it is 90, because we have a triangle, right angle triangle. This is 90, and that means theta and alpha equals 90. So gamma equal 90 minus theta, 90 minus 33, which is 57 degrees. What about alpha? Alpha equals 180 minus gamma. 180 minus 57, which is 123. This is our equation for the formula for the torque. Torque equals N I A B sine alpha. In the book it is theta, but theta, it is the angle between A and B, the normal and the magnetic field. I changed the name from alpha to theta, from theta to alpha, because we have a disturbance theta here. It is misleading. It is not theta that we should put in the equation. Now, because it is a loop, N equals 1, and we have I. Area, it is H times W, B sine alpha. Now substitute. N equals 1. The current is 9. H, it is 6.5 times 10 to the minus 2. W, 4.5 times 10 to the minus 2. B, it is 0.25. Sine 123. Put in your calculator to get the answer. 2 times 10 to the minus 3. It is a torque, so it is a Newton meter. What is the direction of such a torque? This is the normal. This is the magnetic field. If you go from the normal to the magnetic field, you will go through this angle counterclockwise, so the torque is positive, or in out of the page in the positive x direction. In the positive x axis direction. So don't forget the easiest way to find the direction of rotation. Go from the normal vector to the magnetic field strength vector through the smallest angle. This angle, this is the smallest, and this is the largest. I need the smallest one, so I will go counterclockwise, which would be positive. So it is out of the page. If you go to the diagram here, the x-axis is the one that out of the page, positive x-axis. Question number 14. Now we want to apply the right-hand rule as mentioned in Biot-Savart law. Determine the direction of the magnetic field at point A, here. For Biot-Savart, we need to assign a new idea for the right-hand rule. You put the thumb in the direction of the current. Here is the thumb. You extend your index finger with the position vector from the wire to the point that you need to specify the direction of the magnetic field. So the other fingers or the middle finger or the normal to your hand will show you the direction of the magnetic field. So please put the index finger from the wire to point A and the thumb with the current. You will find the magnetic field will be down like this. Okay? Or easily you can put the thumb with the current and curl your four fingers around the current passing through A. So put the thumb in this direction and the other four fingers extend it to the A. Now curl your fingers around the wire. They will go inside then like this. So it is downward at point B. It's easier maybe than the first one. Using the symbols at this diagram, write an expression to find the magnitude of the magnetic field at point A. Now, I have DL for the segment of the wire. To find the magnetic field at point A, put it is like this, mu naught if it is in vacuum or air over 4 pi then I dl as a vector cross r unit vector over r square. This is dB. If you need B, make integration of that one. So it will be like this, and integral this all along the wire. Now, if you need the magnitude, the mu naught over 4 pi I. The magnitude of dl cross r, it is dl r hat, it is 1. The magnitude of r1 is 1 sine theta divided by r squared. That is how to find the magnetic field around this wire. Question number 2. The graph shows a segment of a very long wire. Using the quantities on the graph, write an expression to find the magnetic field at that point, P. It is the same as the previous one, but here we can substitute for theta. And beware, what is theta? It is not this theta. The theta in Biot-Savart law, it is this angle between DL and R. So this is the angle in Biot-Savart law. Biot-Savart law, P as a vector at point P equals mu naught over 4 pi integration I dl cross r hat over r squared. Now, if you need the magnitude, only the magnitude, pp equals mu naught over 4 pi integration I dl cross r hat, again it is 1 as a magnitude, times sine theta for the cross product over r squared. Now it is not theta, it is alpha. Don't forget that, please. It is not every theta in any diagram, it is theta in the equation. Theta in the equation, it is the angle between r hat and l hat. This is the r hat, this is the l hat. This is the angle between them. So it is alpha, not theta. Now, continue with your question. Mu naught over 4 pi. I, it is constant. If it is not constant, you should write the formula of it. dl over r squared. Now for sine alpha, it is the same as sine gamma because they add to 180. Alpha plus gamma equals 180. So sine alpha equals sine gamma. What is sine gamma? It is opposite, which is A, over hypotenuse, which is R, in the triangle here. So put here A over R. And if you change dl into dx, our last formula is, and we will, I will assume that I is constant, so I can get it out. Mu naught I, A, it is a fixed distance, over 4 pi integration dl over r squared, which is dx over r cubed. Now what about r? I can relate it to sine alpha with A and change the integration with respect to alpha or gamma, from minus infinity to minus 90 to plus 90 degrees. Or keep it along the x-axis and make the integration from minus infinity to infinity. You are not asked to find the integration as suggested by the syllabus. Now, number 3, draw at least 3 magnetic field lines around these 2 straight lines carrying current wires. The 2 currents are flowing perpendicular to the page. I have here 2 currents, one outside the paper and the other is inside. I need to draw at least 3 magnetic field lines. First, forget the direction. The magnetic field around the straight wire consists of circles, concentric circles, and if you go away from the wire, the distance or the spacing between the circles becomes larger and larger. So you need to keep this in your mind. Let me use the software to draw good circles for that. I will come back. Something like this. They are concentric circles around the wire. The most important thing when you draw these circles, the spacing of the circles. Look, the spacing from the red one to the green one is less than the spacing between the green and the blue, because as you go away from the wire, the magnetic field becomes weaker, so the distance between the circles become more and more, and the same as this. Look, the shape is the same, but the direction is different. Now, to find the direction of the magnetic field, put your thumb with the current for this one. The current is outside the page, so let your thumb point to you out of the screen. Then your fingers will curl around the wire as counterclockwise in this direction. This is the direction of the magnetic field, and here to the left, here it is down, and here at the bottom it is right, same as this here, here and here, and here and here and here. Now for the second one, the current is inside the screen, so put your finger inside the screen and let your forefinger curl around the wire. Your fingers will curl in this direction. This is the magnetic field here. And here it is up. Here it is to the right. And here it is to the left. Interesting thing that when we invert the current, the magnetic field will be inverted. The magnetic field will be inverted. Opposite current direction means opposite magnetic field directions. Now, the last question for this paragraph. Okay. For this part, express the unit of magnetic field strength in SI units. You can use the magnetic force on the wire as I/L/B sine theta, or the magnetic field on a charge Q/B sine theta. They are the same. Easier one is on the current wire. Newton for the force, the current is ampere, the length is B. We need to find the unit of the magnetic field. Now, the unit of magnetic field, we know it is a Tesla. Now, Tesla is in Newton per meter, for the length, per ampere meter. Okay, but it is not a base unit. A base unit we must get over the Newton. Newton is kilogram meter per second square, over the current is ampere and the length is meter, ampere, meter. Now you can get meter with meter and you are left with kilogram per ampere second square. So the Tesla is in Newton per ampere meter in SI unit, but in base SI unit is kilogram per ampere second square. You can write this Newton ampere inverse 1, meter inverse 1. Here kilogram ampere minus 1 second minus 2. This is plus 2 because it is millimeter. The magnetic field due to the current in a long straight wire is 0.8 Tesla. This is B at a distance of 4 from the center of the wire. What is the current in the wire? Now we suppose that point outside the current, so it's easy to find the magnetic field there. B equals mu naught over 2 by I over V, since it is a very long wire. Mu naught it is 4 by times 10 to the minus 7 for the air or the vacuum over 2 by. The current is unknown. And the distance is 4 centimeters, 4 times 10 to the minus 2. All of this equals to B. What is B? It is 0.8. So our current I equals 0.8 times 2 by times 4 times 10 to the minus 2 over 4 by 10 to the minus 7. By goes with by, 4 with 4. 0.8 times 2, it is 1.6 times 10 to the minus 7, it is 5. There. Now, if you double the current in the wire, where you can find a point at which the magnetic field has half the strength as in part P. Now we double the current, so I, the new I equals double I1, 2 times 1.6 times 10 to the 5, it is 3.2 times 10 to the 5 amperes. We need to find where you can find. So D is unknown. The new D is unknown. With the magnetic field, half of the strength in the part 1. So P2 equals half P1, which is half P1 0.8, it is 0.4 Tesla. We have everything that we need. P equals mu naught over 2 by I over D. I need D. D equals mu I over 2 by B. Substitute 4 by 10 to the minus 7 for mu naught. The new current, I need D2, so I will find I2 and B2. I2, it is 3.2 times 10 to the 5 divided by 2 by times B2, it is 0.4. The answer will be 0.16 meter or 16 centimeters. One can get the answer immediately by proportionality. if you rearrange your law, B equals mu over 2 pi I over D, then D equals mu over 2 pi I over P. This is just a constant, so you can ignore it in the proportionality and write your equation like this: D2 over D1 equals directly proportional with I, so I2 over I1, but inversely with the magnetic field, so P1 over P2. Now substitute. We double the current, so 2I1. I1 remains the same. P1. We halve the magnetic field, so half P1. This is suitable procedure for the proportionality. If you don't know I1 and V1, how you can use this one, you cannot find I2 or B2. But here, if you don't know I2 or I1, B1 or B2, only that you know I2 is something I1, B1 is something B2, so use this procedure. It is very better than that one above. So B2 equals D2 equals 4D1. 4 times 4 centimeters, it is 16 centimeters or 0.116 meters. See you next part. Thank you.
I hope that this video has enriched you more. In the description box below, there are links to both a PDF document for answers and the other videos in this series. This is the end of part 3. See you in part 4. Salam.